Assalamu alaikum, everybody. Welcome to this third lecture. So I'm going to speak about the same chapter number 3, and we have covered a few topics in this chapter. So I'm starting the measures of relative location and the detection of outliers, and later in the chapter we'll be discussing the association and correlation between two variables. So in this session, I'll be speaking about the z-scores, the Chebyshev's theorem, famous empirical rule, and then we'll be detecting a few outliers if there are in the data set. Recall that we are in chapter number 3, and this is the section, this is the relevant section in the book. You should start reading it. So there's a lot of detail that you have to go through. You have to read the chapter, but I'm just going to tell you the summary of the main concepts and the main things. So we will start with the z-scores first. What are z-scores? Z-scores are actually values computed from your data, which will standardize your data. So you can take any data set, be that grouped, ungrouped, any quantitative data set on a ratio or interval scale to a z-score. So the concept of z-scores is pretty simple. Whichever variable you have, so right now if I have a variable x, I should have the mean of x with me, and I should have the standard deviation of x with me if I want to compute the z-score. So z-score is often called a standardized score, and this actually uh, take the difference between the data value from its center, and then it divides that spread on the spread of the data. That's the standard deviation. Okay. So a data value greater than the sample mean will always have a positive value. A data value smaller than the mean will naturally have a negative value. But there's a very important thing about this z-score, that the sum of z-scores is always 0 for any data set. That means that the arithmetic mean of z will always be 0. And another property is that the variance of this z, or the standard deviation of this z for any data, will be equal to 1. So I'll be coming to that a little later. Imagine we had a data set. So this is the same data set for the rental values that was given in the previous two lectures as well. We have computed the standardized values for each of the rental values which was given in our data set. I hope you remember the 70 values that we were given, the rental values that we were given in our data set. So each data value is computed as a z-score. So you can see the z-score is ranging from -1.2 to 2.27. There's another property of the z-score that almost 99% or almost all of the data for a normal data set should be between -3 to +3. So most of the numbers for a standardized variable will fall between -3 and plus. You can see this data set is falling in the same as well. Now, before I start the Chebyshev's theorem, let me just show you a small little illustration of the z-scores. What I have with me is, okay, I have with me a computed z-score example that I want to share with you. So you can see this now. These are the same two questions, the tutorial I had with you for computing the variance, standard deviation, and the coefficient of variation, along with the average in one of my tutorials. You can go back and refer to it. So in this example, I'll be computing the z-score for both of these data sets. They were taken from the book. This was question number 2 and question number 3 from page 110 in the book. This is that data, and we have already computed its mean, its variance, and its standard deviation. And also for this group data, we have computed the same summary measurements. So I have the mean and standard deviation of this data. So I'm computing the z-score here. I'm taking each value and subtracting the mean from it. The mean is 16, and I'm dividing the standard deviation, dividing this difference on the standard deviations. The standard deviation is 3.98, 996 rather. And I've computed all these. Well, now you can see the sum of z-scores is 0. Now this is one property with z-scores, and the sum of z's will always be 0. So they'll be 0 in a non-group data, and they'll be 0 in a group data. You can see this here. But here, because we had frequencies, so we can't, naturally, we can't take only these 4 numbers. These numbers are repeated. So we have to take the repeated z values and then sum them up to get this 0. The second property is that the variance of z score is actually a 1. And let me just try and write this for you here on the screen somewhere, that actually the uh, z z bar, that's the mean of z, will always be equal to 0. That's the first property of any standardized variable. So this is our property number 1. Okay, I'm not very good with writing like this, but still, the second property is, this is our second property, that the variance, sorry about this, the variance of z will always be equal to 1. Just remember this, and these are the two basic properties of a z-score, that the variance will always be equal to 0, as will be equal to 1, and the mean of the z-score will always be equal to 0, no matter which data set you take, no matter how big or small or sample or population or whatever data you take on a ratio or interval scale, you will always get these properties verified. So I've tried the same here. I've computed the z values here, and then I've taken the z-scores sum. Recall that we had the formulas for the variance like this, like you have to, I mean, if I take the open form formula, that was summation zi squared is zi squared, zi squared divided by n minus summation zi, this is zi by n. Okay, so I mean, if I put the values here, I've taken the squares of these z numbers, so I've got the zi squares, and I've summed them. I got 6. So 6, if I divide 6 by the number of observations, I had 6 observations. So 6 by 6 will be equal to 1, minus the summation of z is already 0. So 0 by 6 should be 0, and 6 by 6 is 1. So I get the variance verified to be 1. This was the non-group data. Similarly, in the group data set, if you see, I have these 4 observations. We have already computed the variance standard deviation before. So I'm computing the z value here. So the z value is the same, x minus the mean, which is 3.69, divided by the standard deviation, which is 1.18. So I've computed all these numbers. But see, I'm not summing these 4 numbers because I'm not having 4 numbers. I'm having more numbers. I'm having 19 numbers. So that is why each of these z has to be multiplied with the frequency to get all the z values. So all the z values, if they are summed up, I get a 0. So again, because the mean formula is summation z by n, okay, summation z by n, okay. So you can see that if I put this z, which is 0.00 by 19, so I will end up with 0. So there is the mean of z has to be 0. The variance of z in this case, naturally, I have to take fi zi squared. Here I was just having zi squared, but because I have frequencies here, the squares of z have to be multiplied with the frequency. So I get the summation fi zi squared. So in the formula, this change will come, f will come here as well, and f will come here as well. Because this thing is already 0, I just showed you 0 by 19. and 19 by 19 naturally will give me 1 again. So again, I get the standardized value to be 0. This can be very easily computed in other softwares, like I can do it in SPSS. Let me just quickly glance through SPSS and let me try if I can show you that. Okay, so the software is opening. Let's hope that yes. Okay. Yes, so you can just take a look. Here we are. Let me take the same data value that I had before. So I'm just computing the same 5 values. I'm just copying them from my spreadsheet to the data editor, to the SPSS editor. So let me just take you there. Okay, let me just copy it here. These are the 6 values. I can go to analyze and I can go to descriptives. Click on descriptives. Okay, and select your variable. You can see this save standardized values as variable. So I just want this. I want the standardized values as another variable. So the SPSS editor will hopefully do that for me. The moment I press it, I see this another window popping up, which is actually the finding of my result. But let us just go back to our original data set and let us see if we have gotten our standardized variable as such. Okay, we couldn't get it. I don't know what's the problem, but still, it's quite simple. The standardized variable has it should have been saved. Let me try once more. So descriptors and save standardized variable. Okay, yeah, this time it should happen because previously it was not checked. So okay, let's just go back to our variable view and let's just take a look here. So you can see it here now. The standardized variable has popped up, and you can see that it is already there. So this is my standardized variable. If I compute the variance or standard deviation for this variable, I can very easily find that the mean will be 0. And this time I don't want another thing like the frequency table. I just want the mean and the standard deviation. So I was just checking the variance and the standard deviation for my Z variable. That's it. I don't want anything else. So just click on this and you can see in the findings window that the mean of my data is 0 and the standard deviation is 1 and the variance is 1. So the softwares can help us, and we can do it manually. Now let us go back to our presentation. You can see these scores are computed for our example as well. Now let's come to the Chebyshev's theorem. Now what is the importance of Chebyshev's theorem? Chebyshev's theorem is actually such a theorem that on the basis of the mean and standard deviation, it will determine the data ranges for any kind of data, for any data that quantitative data that we may have. And the theorem states that at least 1 minus 1 by z square or k square, in this case they've written k square, but in the book if you check, instead of this k square they write it z square of the items in any data set will be within z standard deviations of the mean, where z should be a value greater than 1. Okay, so I mean, if I put 2 here, I will get 1 minus 1 by 4, which will be 75%. So 75% of the data should be within 2 standard deviations. If I put k to be 3, So naturally 1 minus 1 by 9 will give me a percentage value of 89%. That should be within 3 standard deviations. And if I put k to be 4, that has to be 1 minus 1 by 16. Do the math here and multiply it by 100, you will get 94% of the items should be within k standard deviations of the mean. Now let's take an example. So for example, for a data set, I think this is the same data set that we've been working with, the apartment rental data. We had the mean of 490.8 and the standard deviation to be 54. You can see we have assumed k to be 1.5. You have to sometimes assume the k and sometimes the z value, or sometimes we may have it. It depends on a number of factors that will come later. So you can see 1 minus 1 by k square will be 56%, and you can see 56% of the data should be within the limits of x bar minus 1.5 times standard deviation, that is x bar minus ks. So you can have 409, if you do the math here, and x bar plus k standard. So there's a plus minus sign. The Chebyshev says that you have to take between the mean plus minus z or k times the standard deviation. So if you do the summation, you get 573. So what we are saying is 56% of the data should be from 409 to $573 of the rents that we had with us. So 56% of the data values should fall between these two rental values, and we can very easily check that by looking at our data. So you can see that this was our actual data, and if you see that the limits that we have gotten were 409 to 573, these are the numbers that we have. Actually, 86% of the rental values are between 409 and 573. So we are taking the numbers from 409 to 573. This one is out. So how many numbers are out? 2, 4, 6, 8, and 10. 10 values are out of our range. We actually had 70 observations. So 10 by 70 should be roughly 14%. They are out of our limits, but 86% are falling in the limits that the Chebyshev is telling us, 409 573. So it's a very handy theorem. Next, we come to the empirical rule. In the empirical rule is another important concept in statistics, in which the previous law that we had, the Chebyshev law, was for any data. You can see this any is marked for us. This applies to any data set, be that normal or abnormal, or no matter what the shape of that distribution is. But with the empirical rule, please remember that this is for a bell-shaped distribution, or this is for a normal distribution or a normal data set. So empirical rule applies only to a normal data set. So that is the main assumption that you should have with any problem that you're facing, or in real life if you want to put an assumption of normality. So the law says that approximately 68% of the values will be within one standard deviation of the mean. So if this is the mean, and you subtract the standard deviation once, and you add the standard deviation once, so naturally a limit will be formed, and this limit will contain approximately 68% of the data value. So that is the concept. And if you take 2 standard deviations of the mean, if you go 2 standard deviations above the mean or 2 standard deviations below the mean, this will cover approximately 95% of the data. So this is what the rule says. And similarly, almost all of the items will be within 3 standard deviations. So if you go 3 standard deviations above the mean and 3 standard deviations below the mean, that will roughly cover the entire data set for us. Okay, so on the same example, this is applied now. You can see that we had the mean and standard deviation with us in our case. So you can see plus minus 1 standard deviation is 436 to 545. That contains 69% of the data values, and within plus minus 2 standard deviation, if we do, this is actually x bar minus 1 standard deviation, and this is x bar um, minus 2 standard deviation, and this is x bar plus 2 standard deviation. Okay, so if you take your calculator and do the math, you will get this interval, and this interval contains 97% of the data, so you can always see the numbers following in between these intervals 97% of the time. And similarly, if you take plus minus 3 standard deviation, that is the mean minus 3 standard deviation, you'll get this number, and the mean plus 3 standard deviation, you get this number. So you can see 326 is the lowest number that you're getting, but here our data starts from 425, and the biggest is 655, and our data ends there. So almost 100% data is covered in this interval. Okay, so the empirical rule is pretty handy in determining the percentage of data in these intervals. Okay, now the next thing that we are going to discuss is that what are outliers? Outliers are extreme data values that will haunt our analysis. We want to get rid of them, or we want to double check them maybe, because they will unnecessarily influence many indicators in our data, and we don't want their influence at times. We may erase them, or we may double check them. I mean, if they're genuine, we would like to keep them, but outlier is something very extreme. So in a data set, if there is an odd observation that you see, or there are maybe a couple of odd observations, many odd observations, that they need to be dealt with statistically. Okay, so conceptually speaking, there are a few methods through which we can detect outliers. Like one very simple method is a data value is declared to be an outlier if it is out of plus minus 3 range. So remember the normality law, or the empirical law that we just witnessed, that was telling us that almost all of the data should be within plus minus 3 standard deviations of the data. So if a data value is out of that range, maybe it is an outlier. Okay? So how outliers creep into the data? They can be human mistakes. Sometimes there are transposition errors. Data is not recorded properly. There are incorrect recordings. People report them incorrectly, or something like that. Okay. So how to detect them? As I've told you, one common method is that search for values that are out of plus minus 3. So for that, you have to compute the z values. The most extreme z values, they have to be computed. So, for that matter, you should have data organized. If the data is organized and you have your observations from very low to very high numbers, so naturally you can find the lowest z number and the highest z number very easily. You can see the lowest is minus 1.2 and the biggest is 2.27. So none of them, none of the data values seems to be an outlier, because all of them are in the absolute free range. Absolute means that they're, forget about the minus sign, from a minus 3 to plus 3, or 3 is that range on either sides that has to be considered for detection of outliers. So in this data set, there is no outlier. Next, we discuss the exploratory data analysis. What is the 5-number summary, and what is the box plot? Box plot is another way of detecting outliers as well, but we'll be first computing the 5-number summary. We have already done this before, but let's just quickly glance through it. The 5-number summary for any statistical data is computing the smallest value, the minimum value, and the largest value. What is the smallest value in the data and the biggest value in the data? And then computing the 3 quartiles. I've already discussed the quartiles with you. So let's just remind ourselves of this. This is the same data that we have been discussing. This is the smallest data value, and this is the largest data value. And then this was our first quartile. This was the average of this was our second quartile, and this is our third quartile. So we have gotten the 5-number summary with us. Now, using this 5-number summary, we can very easily make a box plot. Now, what is a box plot? A box plot is basically a diagram like this one. You can see there's this box in the middle and there are some lines to the left and to the right. Okay, so what are these lines indicating? Actually, this is my first quartile. You can see my first quartile was 450. 450 was my first quartile in the data set. This is my second quartile. My second quartile is 475. Recall in this example, 475 was my second quartile and 450 was my first quartile, and 525 is my third quartile. So let's see, 525 is my, so the box is actually made up of the quartiles. This is quartile number 1, this is quartile number 2, and this is quartile number 3. So just identify on a line your quartiles and make a box out of it. Okay. Now you can see the box is not evenly distributed. This square is small compared to this rectangle. I mean, if I had a line in between, this would have been an even divide. But right now it is not. Usually when you don't have an even divide, that's an indicator of non-symmetry or skewness in the data. So there's a likely skewness in our data set. Okay. Now, how are these dashed lines or these whiskers formed? Okay, for that, we follow a simple formula. Because we are detecting outliers using these quartiles now. So we compute a lower limit, and the lower limit is actually computed from this Q1, and you have to subtract 1.5 of interquartile range. Now, what is interquartile range? Interquartile range is actually the difference between the third and the first quartile. Okay, so how much is the difference between these two numbers? In our case, if you take a look at the first quartile, it is 450. And if you take a look at the third quartile, this is 525. So how much is the difference? 75. Okay, so 75 has to be multiplied with 1.5. Once it has to be subtracted from Q1, and then it has to be added to Q3. So with this Q1, 1.5 of IQR has to be subtracted, and with this Q3, 1.5 of IQR has to be added. Now this will give us numbers to the right or to the left of this data. You can see 337.5 is my lowest value. Okay, 337, you can't see the dashed line coming till this point. It's a little broken here. This should have been here, 337 point. So this is my one line to the left, and this the second whisker is on the right, which is 637. Again, this should follow a bit more. Okay. If any of my data value is out of this interval, my actual data set. So what was my actual data set? This is my actual data set. If any of the number in this data set is out of this range, if it is following below this number or if it is falling above this number, it will be an outlier. So right now, there's nothing, I guess, 337, no, there's nothing to the left, 337. Everything is above 337, so the number is 425, which is far more greater than 337. And then the next one was 637. So just take a look at the data again. 637 again is pretty large. I mean, the number is, so the data is safe, there is no outlier. So using the box and whisker method, this is called the box plot method or the box and whisker method. This is the box and these are the whiskers. My entire data set is in these. So you know that the main thing is computing this lower and upper limit and checking your data in these limits. If it is falling in the limit, there is no outlier. And if any data value is out of these limits. I mean, if you're getting a number below 337.5 or a number above 637.5, they are going to be declared outliers. Okay. The last session of this lecture is about the measures of association between two variables. So up till now, we have been discussing only single variables, but now we are going to discuss the association between two variables. So these are pretty common terms, the covariance and correlation coefficient. But please remember, whenever these terms come, you should have two variables and you're trying to check the association between two variables. So in real life, there could be millions of situations where two variables may be related. For example, our consumption is usually related to our income, or the mileage of a car is naturally it is related to the expenses or the different costs that are incurred in repairing the car. Okay, so there are relationships between variables. I mean, sales are related to advertising expenses, or demand and supply. They are related, things like that. So the positive values will indicate a positive relationship in covariance, and the negative values will indicate a negative. So what is covariance actually? Covariance is a measure of the linear association between two variables. How linearly two variables are associated with each other. That's called a covariance. Okay, so that's like pretty common, like variance. Variance was in a single variable, so covariance has to be in two variables. This is the rule for it. This is how you compute the covariance. So covariance could be computed for a population data or for a sample data. The data could be the whole aggregate. It could be, I mean, theoretically speaking, the whole data set, or just a part of it, a sample. So sample is denoted as S, X, Y, and you can see these are the deviations. But you can see the deviations of X are multiplied with deviations of Y. These are the two variables. And after their multiplication, they're averaged. Averaged in the sense that you're taking the sum and dividing by the number of observations. Remember, with the sample data set, the covariance has to be divided by n minus 1. With the population variance, it has to be a 1. Like we did this in the variance as well. What is the correlation coefficient? Now, correlation coefficient is actually a number between -1 and +1. Covariance will actually measure the intensity of the relationship by a mathematical, a mathematical method, and through a number which is from -1 to +1. So values near to -1 would indicate a strong negative linear relationship, or an exact, if it is exactly -1, an exact negative linear relationship. And if it is +1, an exact positive relationship. But a little lower than +1 or a little lower than -1 will be strong. So the formula usually is pretty much the same. Like you can see, previously we computed the covariance using this formula for the sample. So if you take the same covariance, and if you divide it by the standard deviation of X and the standard deviation of Y, these two are multiplied, take the ratio of the two, you will end up with the correlation. You can do that in the population data as well, and you can do that in the sample data as well. Okay, so correlation and covariance will be thoroughly discussed and will be further examined in the regression and correlation chapter later on. So right now we are not focusing a lot on this, but we're just trying to get the idea here. What was the weighted mean and grouped data? This we have discussed in the tutorial as well. So weighted mean is basically data with weights or with frequencies. Sometimes observations are given along with weights. For example, when we do grocery, we buy things by their weight, for example, in kgs or in pounds, or maybe if you're buying clothes in yards, maybe, or in, you know, the different measurements in milliliters or in cubic feet. So these are the weights usually used for data set, because um, the, the different items that we buy them on a per unit basis price. Okay. So what was group data? Group data is with frequencies. We have already had an example on this. So the sample group data will give me an X bar when the frequencies will come into play. For the populations, likewise, we have the same thing. So this is a data set. You can try this by taking calculator, and you can actually compute this. So you can see the rental values are classified in intervals, and I have the frequency. So 8 rental or 8 houses are in this range of rents, and so on and so forth. So you can take the middle number to be the X value in terms of the computation, or the middle value is denoted by M. So just add the two numbers, divide by 2, you get this middle number, and then multiply this with the frequencies to get the sum. So if I do for all of them, I can do the sum of all of them, which is 34,525 divided by 70. So the value is 493.21, but recall for the ungrouped data, when we computed this figure, it was 490.80. Now think about it, why is this difference coming? And this 2.41 difference from the actual sample, why is this coming? This is only coming because of the organization of the data, that you've classified the data and then you've put the frequencies here. Now, since you're taking the middle numbers, now middle numbers were not the ones which were repeating 8 times or 70. They were just approximate numbers. That is why this difference is coming. But nonetheless, um, you know, this average is pretty close to 490. It's just differing by $3. A variance for the group data, again, ask yourself that, are you doing it for a population data or a sample data? Do you have all of the data, or just a fraction of the data, a subset of the data? The signs have to be different. This is the population variance, and this is the sample variance, but the frequencies are there. There are simplified formula of these theoretical formulas. I mean, we can open this square like a square plus b square minus 2ab, do a little bit of algebra, and we can have simplified versions of this or this formula. You can try this, they're in the books as well. They're pretty simple, you can easily understand them. But let's try this, and you know, using our data, how to do this. So this was your data. Okay, you have to do a few more calculations. I mean, if you still do not get these formula, watch my tutorial on how to compute the variance, standard deviation, and coefficient of variation. Hopefully you will get it. So this brings us to the end of this chapter. I've tried to cover the whole chapter by giving a lot of time to the important concepts. Read the book thoroughly. If you have any questions, note them down, and whenever we are online or in the class, do not hesitate to ask me those questions. Best of luck.